Hello there, and welcome to the Sleeping Physicist. If you're someone who likes to unwind by thinking about stars, particles, and the quiet structure of the universe, you're in the right place. Tonight, we'll let our attention drift gently into real physics and real discoveries. Some of what you'll hear may feel surprising, but all of it is grounded in what we've carefully learned about nature. And if you enjoy these slow explorations, you're welcome to like and subscribe. But for now, let your body rest, let your thoughts loosen their grip, and let's begin. What is frequency made of according to quantum physics? If you listen carefully to the room around you, there are small rhythms unfolding right now. The soft hum of distant electricity, the faint movement of air. Even your breathing carries a gentle repetition. Something rises, something falls, then it rises again. Frequency is how often that repetition occurs within a stretch of time. It is the count of cycles per second, a simple measure of return. When a guitar string vibrates, it does not stay displaced. It moves back toward its resting position, passes through and swings outward again, back and forth, back and forth. Each complete motion defines one cycle. The number of these cycles within a second gives the frequency of the note you hear. The pitch is not the wood, it is not the metal string. It is the rate at which motion repeats. Sound in the air works the same way. Tiny compressions and rarefactions travel outward from a source. The air itself does not travel across the room in a steady stream. Instead, it oscillates locally. Pressure increases, then decreases, then increases again. The ear interprets the speed of this repetition as tone. Light behaves with the same underlying structure. The color of light is determined by how quickly the electromagnetic field oscillates. Red light corresponds to slower oscillations. Blue light corresponds to faster ones. Nothing solid changes its pigment. What changes is the rate of field variation in time. So at the level of experience, frequency does not describe a material substance. It describes a pattern, a rhythm, a structured recurrence. Already we see something subtle. Frequency cannot be held. It cannot be broken into fragments like grains of sand. It is not built from smaller physical pieces. It is defined by how a system changes and returns in time. If there were no change, there would be no cycle. If there were no cycle, there would be no frequency. And if there were no time through which change could unfold, repetition could not be counted. Frequency, at the level of direct observation, is organized repetition within time. It is the measurable rhythm of motion returning to itself. If frequency is repetition, then repetition quietly depends on something deeper. A cycle only makes sense if there is a before and an after. A vibration requires duration. Even the idea of counting demands that moments pass in sequence. So beneath every frequency lies time itself. When we say a string vibrates 400 times per second, we are not only describing the string, we are invoking a steady background against which those 400 events can unfold. Without that steady progression, there would be no way to distinguish one oscillation from the next. Time provides separation. It allows change to occur in ordered steps. It allows motion to return and be recognized as return. Imagine freezing the universe entirely. No ticking clocks, no shifting fields, no evolving systems. In that stillness, the concept of frequency disappears. Not because the vibrating object vanishes, but because vibration requires temporal unfolding. Without time, repetition cannot extend. Without extension, cycles cannot form. So frequency is not independent. It rests upon temporal structure. In everyday life, time feels uniform. Seconds pass steadily whether we notice them or not. This steady flow becomes the measuring stick for oscillation. We compare motion against this background and assign a rate. But physics teaches something careful here. Time is not merely a human invention for tracking events. It is woven into the structure of reality. Every process unfolds along this dimension. Every change occupies duration. Frequency, then, is not built from matter. It is built from change distributed across time. And change itself is never random in oscillatory systems. It follows a pattern. There is a restoring influence. A displaced string is pulled back by tension. Compressed air pushes outward because pressure differences seek balance. The system carries an internal rule that governs its return. Time allows that rule to operate step by step. So what we call frequency is already more than counting. It is structured motion unfolding across a continuous temporal dimension. The rhythm is inseparable from the passage that allows it to be expressed. Frequency depends on time as its silent foundation. Without time, there is no repetition. Without repetition, there is no frequency. What holds steady beneath the rhythm is the ordered progression of moments that permits change to recur. Once time provides a stage for repetition, we can look more closely at what actually repeats. In classical physics, oscillation emerges whenever a system is displaced from balance and a restoring influence guides it back. A pendulum swings because gravity pulls it toward its lowest point. A stretched spring snaps inward because tension resists distortion. Each system carries within it a tendency toward equilibrium. When displaced, the system accelerates toward balance, but momentum carries it past that balance point. The restoring influence then reverses direction, pulling it back again. This interplay between inertia and restoration creates a smooth back and forth motion. Nothing mysterious is required. 2 ingredients are sufficient. There must be something that resists change, and something that pushes the system toward its preferred configuration. Together, they produce sustained oscillation. Water waves reveal the same pattern. Gravity pulls the surface downward. Pressure differences push it upward. The surface rises and falls because these influences continuously trade dominance. Energy shifts between motion and position in a steady exchange. In these classical systems, frequency emerges from physical properties. A tighter string vibrates faster because stronger tension increases the restoring pull. A heavier mass vibrates more slowly because greater inertia resists acceleration. The rate of repetition reflects the balance between these opposing tendencies. Frequency here is not an abstract label. It is determined by structure. Change unfolds according to measurable physical constraints. This already refines our earlier understanding. Frequency is not made of tiny pieces. It arises from the interaction between inertia and restoration within a system extended in time. The rhythm is governed by the rules embedded in matter and force. As long as those rules remain constant, the oscillation continues with predictable regularity. The system carries within it the conditions that fix its rate of repetition. Classical physics shows that frequency is shaped by structure. It is the stable rhythm that emerges when forces and motion interact under consistent laws. When a system oscillates, something deeper than motion is taking place. Energy is not static within the cycle. It shifts form in a continuous exchange. When a pendulum reaches the top of its swing, it momentarily pauses. Its energy is stored in position. As it falls, that stored energy transforms into motion. At the lowest point, motion is greatest. Then the process reverses. Oscillation is a conversation between different expressions of energy. A vibrating string behaves the same way. When it bends away from its resting position, energy is stored in tension. As it snaps back through equilibrium, that stored energy becomes kinetic motion. Neither form dominates permanently. They trade places in a steady rhythm. Frequency emerges from how quickly this exchange completes itself. If the restoring influence is strong, energy converts rapidly between forms. The cycle completes in a shorter duration. The frequency increases. If inertia dominates, the exchange unfolds more slowly. The frequency decreases, so the rate of repetition reflects the tempo of energy transformation inside the system. This reveals something important. Frequency is not an additional ingredient layered on top of matter. It is the visible trace of energy reorganizing itself through time. The cycle is energy flowing between complementary states under constraint. Nothing material is being consumed in this process. The system retains its total energy. What changes is its configuration. Oscillation is structured energy movement that repeats because the underlying forces remain constant. In classical physics, this structure is continuous. Energy can take on any value. Oscillation can, in principle, be reduced smoothly towards stillness. The amplitude shrinks, the motion becomes smaller. Eventually, friction removes the organized exchange and the cycle fades. But before that fading occurs, frequency remains defined by the balance between stored energy and motion. It is governed by how rapidly the system can shift from one form to the other. Frequency, in this classical picture, is the rate at which energy completes a full transformation cycle within time. It is determined by physical structure and conserved by the laws that govern motion. So far, oscillation has appeared in tangible systems. Strings vibrate, pendulums swing, water surfaces rise and fall. Each case involves matter shifting under forces. But light introduces something more subtle. Light does not require a string. It does not require air. It does not require a surface to ripple. It travels through empty space, and yet it oscillates. Classical electromagnetism revealed that space itself can host dynamic activity. Electric and magnetic fields are not merely mathematical tools. They are physical entities that can change and propagate. When an electric field varies, it generates a magnetic field. When a magnetic field varies, it generates an electric field. Each sustains the other. This mutual generation allows an electromagnetic wave to move forward without any material medium. The oscillation is carried by the fields themselves. At every point in space that light passes through, the electric field rises, falls, reverses direction, and repeats. The magnetic field does the same, oriented perpendicularly. Nothing material travels from source to destination in the classical sense. What propagates is structured field variation. The color of light is determined entirely by how rapidly these fields oscillate. A slower oscillation corresponds to red light. A faster oscillation corresponds to blue. The frequency defines the identity of the radiation. This shifts our understanding. Frequency is no longer tied exclusively to mechanical motion. It can describe the behavior of something more fundamental than matter. A field can oscillate without requiring particles to swing back and forth. In empty space, there is no string under tension and no air to compress. Yet frequency remains meaningful because the electromagnetic field itself possesses structure. It carries energy. It evolves through time according to precise equations. Its oscillation rate is fixed by the conditions of its propagation. Here, frequency is the rate at which a field's strength changes sign and returns. It is embedded in the evolution of the field at every point it touches. So even before quantum physics enters the story, frequency has moved beyond visible objects. It describes the temporal rhythm of fields that permeate space itself. The repetition belongs to the field's evolution in time, governed by consistent physical laws. When electromagnetic waves were first studied carefully, a quiet pattern emerged. The faster the oscillation of the field, the more energy the radiation carried. Blue light can trigger chemical reactions that red light cannot. Ultraviolet radiation can break molecular bonds that visible light leaves untouched. X-rays penetrate matter more deeply still. The difference is not brightness alone, it is frequency. At first, classical physics assumed that energy could be transferred continuously. A wave with a certain amplitude would carry a corresponding amount of energy, and that energy could be divided as finely as desired. Frequency influenced behavior, but it was not seen as fundamentally tied to energy in discrete terms. Then a puzzle appeared. When light strikes certain metals, electrons can be ejected from their surfaces. This phenomenon became known as the photoelectric effect. What startled physicists was not that electrons were released, but how the release occurred. Increasing the brightness of low-frequency light did not eject electrons if the frequency was below a certain threshold. No matter how intense the wave became, the electrons remained bound. Yet a dim beam of higher frequency light could eject them immediately. Energy transfer was not behaving as a smooth classical wave. The crucial discovery was that energy carried by light arrives in packets, whose size depends directly on frequency. Higher frequency means larger energy per packet. Lower frequency means smaller energy per packet. The proportionality is precise. The energy of each packet equals a constant multiplied by the frequency. That constant is known as Planck's constant. This relationship transforms our question. Frequency is no longer merely a rate of oscillation in time. It directly determines how much energy is contained in each quantum of radiation. The rhythm of the field is inseparable from the amount of energy it can deliver. Energy and frequency are locked together. The faster the field oscillates, the greater the energy bound to each excitation. The slower the oscillation, the smaller the energy carried. Frequency, then, is not only about repetition, it is about how energy is structured within that repetition. In quantum physics, the tempo of oscillation sets the scale of energy itself. The discovery that energy arrives in packets tied directly to frequency required a deeper revision of how oscillation itself is understood. Max Planck first encountered the problem while studying how heated objects emit radiation. Classical predictions suggested that energy at high frequencies should grow without limit. Experiments did not agree. The emitted spectrum followed a very specific curve that classical theory could not reproduce. Planck resolved the mismatch by making a careful and radical assumption. The oscillators inside matter that emit radiation could not exchange energy continuously. They could only change their energy in discrete steps. Each step was proportional to the frequency of oscillation. This was not an aesthetic choice. It was a constraint imposed by observation. The constant of proportionality, now called Planck's constant, set the scale of these steps. It introduced a new unit into physics, not a unit of length or time, but a unit of action. Action combines energy and time. It measures how much energy is involved over a duration. This constant fixed the size of the smallest possible change in energy for a given frequency. If an oscillator vibrates with a certain frequency, its energy cannot slide smoothly to any value. It must occupy specific allowed levels separated by equal intervals. The spacing between these levels depends directly on the frequency itself. Higher frequency means larger gaps between energy levels. Lower frequency means smaller gaps. So frequency does not simply accompany energy. It sets the quantization scale of energy. The oscillation remains, but it is no longer continuous in its energetic possibilities. The rhythm persists in time, yet the allowed energies associated with that rhythm come in discrete amounts. This introduces a new layer to our question. If frequency determines the size of energy quanta, then frequency is embedded in the structure of quantum transitions. It governs how systems can absorb or emit energy. It shapes the ladder of possible states. Frequency, at the quantum level, becomes the organizing principle that determines how energy is partitioned. It fixes the discrete steps by which physical systems can change. Once energy exchange is restricted to discrete steps, the familiar image of a smoothly vibrating system begins to shift. Consider the simplest possible oscillator, a mass attached to a spring. In classical physics, this system can possess any energy value. The amplitude can shrink continuously. The motion can become arbitrarily small. Nothing prevents the oscillator from settling perfectly at rest. Quantum physics does not allow this smooth descent. When the same system is described using quantum principles, its energy is confined to specific allowed levels. These levels are evenly spaced. The spacing between them is determined by the frequency of the oscillator itself. The faster the natural oscillation, the larger the separation between adjacent energy levels. This means the oscillator cannot possess just any amount of energy. It must occupy one of these permitted states. If energy is removed from the system, it cannot decrease in an unbroken glide. It must drop from one level to the next lower one. Each drop corresponds to the emission of a quantum of energy whose size is fixed by the oscillator's frequency. The rhythm of oscillation has now become embedded in the very architecture of possible states. Even more striking, the lowest permitted energy is not zero. Classically, the system could rest completely still. In quantum physics, the oscillator retains a minimum energy even in its lowest state. It cannot be stripped of all motion. This residual energy is called zero-point energy. The reason lies in the structure of quantum uncertainty. Position and momentum cannot both be specified exactly. If the oscillator were perfectly still at equilibrium, both its position and momentum would be precisely defined. Quantum rules forbid that configuration. So even at its lowest energy, the oscillator retains a subtle fluctuation. Not a classical vibration with a well-defined amplitude, but an intrinsic dynamical presence enforced by quantum law. This changes our understanding of frequency once again. Frequency is no longer just the rate of visible motion. It determines the spacing of allowed energies. It sets the scale of unavoidable ground state activity. It governs how systems step between possibilities. Oscillation remains, but it is now woven into the discrete structure of reality. Frequency fixes the pattern by which energy is permitted to exist. That unavoidable ground state motion deserves to be felt more carefully. In classical thinking, stillness is simple. Remove energy and motion fades away. The pendulum hangs motionless. The spring rests at equilibrium. Zero energy corresponds to complete quiet. Quantum physics does not permit that absolute quiet. When an oscillator reaches its lowest allowed energy level, it does not become frozen. Instead, it occupies a state in which position and momentum remain subtly spread out. The system cannot sit precisely at the center with zero velocity. The uncertainty principle prevents both quantities from becoming exact simultaneously. If position were perfectly fixed, momentum would become infinitely uncertain. If momentum were perfectly zero, position would blur without limit. The ground state finds balance between these constraints. This balance creates what is called zero-point energy. It is not extra energy added from outside. It is the minimum energy required for the system to remain consistent with quantum structure. Even in its calmest state, the oscillator retains motion in a statistical sense. The expectation values remain steady, but fluctuations persist. The system cannot collapse into perfect rest because the fabric of quantum mechanics does not allow complete determinacy. The frequency of the oscillator determines the size of this ground state energy. Higher frequency oscillators possess larger minimum energies. Lower frequency oscillators retain smaller ones. Once again, frequency sets the scale. This reveals something subtle about what frequency governs. Frequency is not merely the visible pace of vibration. It fixes the spacing between energy levels and the unavoidable baseline energy present, even when no transitions occur. It shapes the internal architecture of stability itself. So when we ask what frequency is made of, we begin to see that it is not assembled from components. It acts as a parameter that determines how a quantum system is structured across its possible states. Even in stillness, the influence of frequency remains active. It defines the lowest possible energy consistent with quantum law. The rhythm is encoded into the ground state of the system. Up to this point, oscillation has been described in terms of systems: a spring, a pendulum, an electromagnetic wave traveling through space. But quantum physics gradually revealed that the most fundamental layer of reality is not built from small solid objects vibrating in empty space. Instead, the foundation appears to be fields. A field assigns a value to every point in space and time. The electromagnetic field has a strength and direction everywhere. The gravitational field shapes the geometry of space-time itself. In quantum theory, every type of particle corresponds to its own underlying field that permeates the universe. Electrons are associated with an electron field, quarks with quark fields, photons with the electromagnetic field. These fields are not additions placed on top of space. They are woven into its structure. When nothing observable is happening, the fields do not vanish. They settle into their lowest energy configurations. Even then, subtle quantum fluctuations remain because zero-point energy cannot be removed. What we perceive as particles are not tiny independent beads. They are localized excitations of these fields. A photon is a discrete excitation of the electromagnetic field. An electron is a discrete excitation of the electron field. This reframes oscillation once more. When we speak of light having a frequency, we are describing how the electromagnetic field evolves in time at each point in space. When we speak of a quantum harmonic oscillator, we are describing allowed energy states of a field mode. The underlying entity is not the particle, but the field itself. Fields possess intrinsic dynamical rules. They evolve according to equations that determine how their values change from moment to moment. Oscillation arises naturally when the field configuration supports repeating patterns in time. So frequency, at the deepest level we have reached so far, is the rate at which a field configuration cycles through its allowed variations. It is not the shaking of a tiny object. It is the temporal evolution of a field that exists everywhere. Quantum physics replaces the picture of vibrating matter with the picture of structured fields whose excitations carry discrete energy determined by frequency. The rhythm belongs to the field's evolution across time. Once fields are treated as fundamental, the idea of a particle changes its meaning in a quiet but decisive way. A particle stops being a tiny object moving through emptiness. It becomes an event the field can sustain, a stable, countable excitation, a discrete way the field can hold energy and momentum without smearing into nothing. You can picture a field as something more like an ocean than a stage, not because it is made of water, but because it can support patterns that travel, overlap, and persist. A classical wave is one kind of pattern. It can have any amplitude. It can be made smaller and smaller without limit. That smoothness is exactly what quantum theory replaces. In quantum field theory, the field does not accept every possible amount of excitation. It has permitted modes, and those modes come in indivisible units. When the electromagnetic field is excited in one of its allowed modes, the excitation is not arbitrary. It is counted. 1 unit is called a photon. 2 units are 2 photons. The field is not slowly filling up like a dimmer switch. It is stepping between integers. This is where frequency becomes structurally important again. A field can be decomposed into modes, and each mode behaves like an oscillator. Not a literal spring, but a degree of freedom that can store energy in a repeating pattern through time. Each mode has an associated frequency set by the geometry of the situation and the constraints on the field. Put the field in a cavity, and only certain standing wave patterns fit. Each pattern has its own frequency. In open space, the spectrum is continuous, but each plane wave component still carries a definite frequency. Now the earlier quantum rule returns, but in a more universal form. Each mode's energy can only take values in discrete steps, and the size of each step is set by its frequency. One excitation of that mode carries an energy proportional to that frequency. Higher frequency modes have larger quanta. Lower frequency modes have smaller quanta. This is not a feature of light alone. It is how quantized fields store energy at all. So when we speak of a photon's frequency, we are not describing a little bead that wiggles quickly. We are identifying which field mode is excited, and therefore what the size of the energy step must be. Frequency labels the mode, and the mode determines what an individual excitation costs in energy. Even the notion of one particle becomes a statement about counting excitations of a specific frequency mode of a field. A particle, in this view, is not a separate ingredient added to the universe. It is the field taking on a discrete amount of organized oscillatory energy. Frequency is the signature of that organization, and the quantization makes the organization countable. If a particle is a discrete excitation of a field, then what exactly is oscillating? The field itself evolves in time. At every point in space, the field has a value. That value does not remain frozen. It changes according to precise dynamical laws. In many situations, those changes take the form of oscillations. The field increases, decreases, reverses sign, and repeats. This temporal variation is what we recognize as frequency. But now the idea must become more exact. In quantum theory, each allowed mode of a field behaves mathematically like an oscillator. Its state evolves with a specific temporal rhythm. That rhythm is not imposed from outside. It arises from the field's own internal structure and the constraints of space-time. Frequency, at this level, is the rate at which the phase of that field mode advances in time. Phase is a way of tracking where the system is within its cycle. When a sine wave completes one full oscillation, its phase has advanced by a full turn. If the oscillation is faster, the phase advances more rapidly. If the oscillation is slower, the phase progresses more gently, so frequency measures how quickly the internal clock of a field mode ticks forward. This is not motion through space in the ordinary sense. Even a standing wave fixed in place carries frequency because its phase evolves. The value of the field at each point changes in a coordinated way. The pattern may remain spatially stable, but temporally it rotates through its cycle. When a photon is present, the electromagnetic field mode associated with that photon is excited. Its phase evolves at a rate fixed by its frequency. That rate determines the energy of the excitation. The oscillation is encoded in the time dependence of the field's quantum state. Nothing additional needs to be inserted to make frequency happen. It is built into the time evolution of the field itself. So when we ask what frequency is made of, we move closer to the foundation. Frequency is not composed of smaller parts. It is the measurable rate at which a field's phase changes with time. It is the tempo of quantum evolution written directly into the field's behavior. Once frequency is understood as the rate at which phase advances, phase itself becomes physically meaningful. In classical waves, phase can feel like a bookkeeping device. It tells us where we are in a cycle. But in quantum physics, phase is not merely descriptive. It governs how systems combine and interfere. A quantum state evolves in time according to a precise rule. If a system has a definite energy, its state acquires a time-dependent phase factor. That phase rotates steadily. The speed of that rotation is proportional to the energy of the state. Because energy and frequency are directly proportional, the phase advances at a rate set by frequency. This rotation does not represent a particle spinning in space. It is a rotation in an abstract space that encodes the system's possible configurations. Yet its consequences are measurable. When two quantum states overlap, their phases matter. If their phases align, the probabilities reinforce. If their phases oppose, the probabilities diminish. Interference patterns arise not from solid objects colliding, but from the structured addition of evolving phases. So the phase evolution of a quantum state carries observable weight. The frequency attached to a state determines how rapidly its phase turns. If two states have slightly different frequencies, their relative phase slowly drifts. This drift produces oscillations in measurable quantities. Transitions between energy levels can be driven when an external field matches the difference in frequency between states. Everything remains governed by temporal evolution. Frequency is therefore embedded directly in the equation that describes how quantum states change with time. It fixes the rate at which the internal phase advances. That phase in turn determines how amplitudes combine and how probabilities unfold. What appears experimentally as absorption lines, emission spectra, and interference fringes can all be traced back to phase relationships evolving at specific frequencies. Frequency is not added onto quantum systems as an accessory. It is the parameter that sets the pace of their time evolution. The rotation of phase in quantum state space proceeds at a rate defined by frequency, and that rotation governs measurable behavior. When phase evolves in a quantum system, it does not describe a visible oscillation in space like a vibrating string. It governs something quieter, but just as real. It governs probability. In quantum mechanics, the state of a system is represented by a wave function. This wave function is not a physical wave like water or air. It encodes the probability amplitudes for different outcomes. Yet it evolves in time with a definite frequency whenever the system has a definite energy. The phase of this wave function rotates steadily. That rotation is not directly observable. What becomes observable is the way multiple amplitudes combine. If two possible paths lead to the same outcome, their amplitudes add. If their phases align, the probability increases. If their phases oppose, the probability decreases. Interference arises from phase differences evolving at specific frequencies, so frequency shapes the rhythm of probability itself. Consider an atom with two allowed energy levels. Each level has its own frequency of phase evolution, because each has its own energy. When the atom is placed in a superposition of those levels, the relative phase between them changes in time at a rate equal to the energy difference divided by Planck's constant. That rate is a frequency. As this relative phase evolves, measurable quantities oscillate. The probability of finding the system in one configuration or another shifts predictably. These are not mechanical vibrations. They are oscillations in likelihood. When external radiation matches that frequency difference, transitions become efficient. The atom absorbs or emits energy precisely because the driving field oscillates in synchrony with the system's internal phase evolution. Nothing material is colliding in the classical sense. Instead, phase relationships align and energy exchange becomes allowed. Frequency, at this depth, is the rate at which probability structure rotates in time. It governs when constructive alignment occurs. It governs when destructive cancellation suppresses outcomes. It determines resonance conditions that make quantum transitions possible. So frequency is not made of smaller building blocks. It is embedded in how the wave function evolves. It is the tempo at which the geometry of probability space turns. The physical world we measure emerges from these evolving phase relationships. What appears stable or dynamic in experiment traces back to frequencies encoded in quantum state evolution. The rhythm belongs to the time dependence of probability itself. So far, frequency has appeared wherever there is oscillation, energy quantization, and phase evolution. It determines the spacing between energy levels. It governs how wave functions rotate in time. It fixes how probability interferes. Now something even more fundamental emerges. Energy itself carries frequency. Relativity tells us that energy and mass are equivalent. A particle at rest still possesses energy because of its mass. That energy is not kinetic. It is intrinsic. Even when nothing is visibly moving, the system carries an energy equal to its mass, multiplied by the square of the speed of light. Quantum mechanics links energy and frequency directly. Energy equals Planck's constant multiplied by frequency. If energy implies frequency, and mass implies energy, then mass implies frequency. This means that even a particle sitting completely still in space has an associated intrinsic frequency. Not because it is vibrating mechanically, but because its quantum state evolves in time with a phase rotation determined by its rest energy. An electron at rest carries an enormous internal frequency. The number is far beyond anything we perceive directly, but mathematically it is precise. Its wave function rotates in phase at a rate proportional to its mass energy. Nothing is visibly oscillating in space. There is no shaking object. Yet time evolution continues. The internal phase advances relentlessly. This deepens the meaning of frequency further. Frequency is not only a property of radiation or excited states. It is tied to the existence of energy itself. Wherever there is energy, there is phase evolution. Wherever there is phase evolution, there is frequency. Mass is therefore associated with a kind of internal clock. Not a clock that ticks in space, but one that rotates in the abstract space of quantum states. This rotation is continuous and unavoidable. When particles move, their observed frequencies shift according to relativity. Time dilation alters the rate at which internal phase evolves relative to an external observer. Frequency and time are inseparable at this level, so frequency is embedded in the union of quantum mechanics and relativity. It expresses how energy manifests as temporal evolution. It is not constructed from components. It is the direct expression of energy unfolding in time. Wherever mass and energy exist, frequency exists as the rate of phase advance dictated by fundamental constants. Before we complete the structure, something must be cleared away. Frequency is not a substance. It is not made of smaller oscillations stacked together. It is not composed of micro vibrations inside larger vibrations. It is not built from pieces the way matter is built from atoms. There is no deeper granularity beneath frequency waiting to be uncovered. The temptation to imagine frequency as made of something comes from how we think about physical objects. Objects are assembled from parts. Molecules are built from atoms. Atoms are built from subatomic particles. We grow used to the idea that explanation means reduction into smaller components. But frequency does not belong to that category. Frequency is a rate. A rate is not a thing. It is a relationship between change and time. When a field evolves, its phase rotates. That rotation has a speed. That speed is frequency. If the evolution is faster, the frequency is higher. If the evolution is slower, the frequency is lower. Nothing is being assembled to create that rate. It is simply how quickly the system moves through its allowed configurations. Even in quantum field theory, where particles are excitations of underlying fields, frequency does not sit beneath those excitations as a smaller ingredient. Instead, it characterizes the mode of excitation itself. A given field mode has a definite temporal behavior. Its frequency defines how rapidly its state evolves. So when we ask what frequency is made of, we are already leaning on a category mistake. Frequency is not built from elements. It is a descriptor of evolution. Energy is tied to frequency because energy determines how fast phase rotates. Mass is tied to frequency because mass is a form of energy. Probability oscillates because relative phase evolves at specific frequencies. In every case, frequency appears as the measurable rate of change of a system's internal state over time. If time did not exist, frequency would not exist. If change did not occur, frequency would not exist. But frequency itself does not require additional structure beneath those two ingredients. It arises wherever change unfolds in time according to stable laws. So frequency is not a hidden material layer of reality. It is the quantitative expression of temporal evolution. It is the countable measure of how quickly a physical system advances through its cycle of states under the constraints of quantum law. There is one more layer that must be uncovered before the picture stabilizes. In quantum physics, frequency is not merely something that happens within time. It is mathematically connected to the operation that shifts a system forward in time. Every physical system has a rule that tells it how to evolve. This rule is encoded in what is called the Hamiltonian, the operator associated with energy. The Hamiltonian generates time evolution. If you apply it to a quantum state, it determines how that state changes from one moment to the next. Energy is the generator of time translation, but energy and frequency are proportional. That proportionality is exact and universal. So wherever energy generates temporal evolution, frequency measures the rate of that generation. This means frequency is not sitting passively inside a system. It expresses how strongly the system advances through time. If a state has higher energy, its phase rotates faster. That faster rotation is not cosmetic. It is the direct manifestation of how time evolution operates. The system is not merely sitting in time. It is being carried forward by a generator whose strength is measured as frequency. In this sense, frequency is tied to symmetry. Physics contains a deep principle. Whenever a system has a symmetry, there is a conserved quantity associated with it. If the laws of physics do not change from one moment to the next, then time translation symmetry exists. That symmetry gives rise to conservation of energy. Frequency is the measurable imprint of that symmetry. Because energy is conserved under time translation, the rate of phase rotation remains steady for a stationary state. The constancy of frequency reflects the uniformity of time itself. If time were uneven or unstable, frequencies would drift unpredictably, but they do not. Their stability reveals the structure beneath them, so frequency is not made of parts. It is the operational expression of time translation symmetry in quantum systems. It measures how the generator of time acts on a state. It expresses the strength of temporal progression encoded in energy. Frequency is therefore not simply a property inside time, it is how physical systems participate in time's uniform advance. Now the structure tightens. If energy generates time evolution, and frequency measures the rate of that evolution, then frequency is not something that sits inside a system waiting to be decomposed. It is already the measure of how the system advances through time under its own energy. To reduce frequency further would mean asking what generates the rate at which time translation occurs. But in quantum theory, energy is the generator of time translation by definition. There is no deeper mechanical gear turning beneath it. The relationship is structural, not composite. When a quantum state evolves, its phase changes according to its energy. That energy fixes the frequency. The frequency is not built from smaller oscillations hiding underneath. It is the direct mathematical expression of time symmetry acting on the state. If we tried to imagine frequency being made of smaller frequencies, we would immediately face a problem. Those smaller frequencies would also require time in which to unfold. They would require their own rates of phase evolution. The explanatory chain would not terminate in parts. It would circle back to time and change. So the reduction stops here. Frequency belongs to the level of description where time and energy meet. It expresses how quickly a system moves through its allowed configurations because of the energy it possesses. That is not a layered structure. It is a fundamental relationship between conserved quantity and symmetry. In classical mechanics, you can imagine gears turning beneath motion. In quantum field theory, the turning is the evolution of the state itself. There is no smaller mechanism beneath the rate of phase rotation. The phase evolution is the mechanism. Even mass, which once seemed like solid substance, resolves into energy, and energy resolves into the generator of time evolution, and the strength of that generation is measured as frequency. The chain does not continue downward into smaller building blocks. It resolves into structure. Frequency cannot be reduced further because it is not assembled. It is the quantitative measure of how physical reality advances in time under the constraint of conserved energy. That relationship is foundational within our current understanding of quantum theory. Nothing deeper is required to make frequency operate. It is already the expression of how time and energy are bound together. When frequency is seen as the rate of phase evolution generated by energy, something profound becomes visible. Time is not separate from this structure. In relativity, time is woven together with space into space-time. Different observers moving relative to one another do not agree on durations. A moving clock ticks more slowly relative to a stationary one. Gravitational fields also alter the rate at which time passes. Near a massive body, clocks run more slowly than far away. These are not illusions. They are measurable consequences of space-time geometry. Now combine this with what quantum theory tells us. A particle at rest has an intrinsic frequency associated with its rest energy. That frequency reflects how quickly its internal quantum phase evolves. If the particle begins to move, relativity tells us that time for that particle flows differently relative to an external observer. Because time dilation occurs, the observed rate of phase evolution shifts accordingly. Frequency transforms with motion. This is not an added correction layered on top of quantum behavior. It is the natural consequence of energy being the generator of time translation within a space-time whose geometry is dynamic. The internal phase of a quantum system advances along its own proper time, the time measured along its world line. If that proper time slows relative to another observer, the frequency observed also shifts. This is why moving particles exhibit relativistic frequency changes. It is why gravitational redshift occurs. Light climbing out of a gravitational well loses frequency because time itself is passing differently in that region. So frequency is not merely the rate of oscillation inside a fixed universal clock. It is the local rate of quantum phase evolution measured against space-time structure. Quantum mechanics binds frequency to energy. Relativity binds energy to space-time geometry. Together, they reveal that frequency expresses how energy evolves within the geometry of time itself. There is no deeper substance beneath this. Frequency is how the universe keeps track of energy as it moves through space-time. It is the measurable imprint of time's geometry acting on quantum phase. When space-time curves, frequency shifts. When velocity changes, frequency shifts. Yet the underlying rule remains stable. Energy generates phase evolution, and phase evolution defines frequency within the local flow of time. Frequency is therefore not isolated from gravity or motion. It participates in the fabric of space-time. It reflects how quantum systems inhabit time according to the geometry of the universe. Now, the pieces settle into place. We began with a simple observation, a vibration, a repetition, a rhythm unfolding in time. At first, frequency seemed like a count, a tally of cycles per second, something almost mechanical. But each layer we uncovered moved the meaning deeper. Classical physics showed that frequency arises from structure. A balance between inertia and restoring influence produces oscillation. The rate of repetition reflects the physical constraints of the system. Frequency is shaped by law. Quantum physics then reshaped oscillation itself. Energy could no longer vary continuously. It came in discrete steps. The size of those steps was set by frequency. Oscillators retained unavoidable ground state energy determined by their frequency. Particles revealed themselves as excitations of fields, and each field mode carried a definite frequency tied directly to its quantized energy. Then the structure tightened further. Energy determines how a quantum state evolves in time. That evolution appears as phase rotation. The speed of that rotation is frequency. Frequency is not an object vibrating. It is the measurable rate at which phase advances under the influence of energy. Mass carries energy. Therefore, mass carries intrinsic frequency. Even a particle at rest evolves in time through internal phase rotation. Relativity then shows that time itself depends on motion and gravity. Because frequency measures evolution in time, it shifts when time shifts. Gravitational redshift and time dilation are not separate phenomena layered on top. They are direct consequences of frequency expressing energy's relationship with space-time. So what is frequency made of? It is not composed of smaller oscillations. It is not built from hidden microstructures. It is not a substance beneath matter. Frequency is the rate at which physical systems evolve in time due to the energy they possess. It is the quantitative expression of time translation symmetry. It is how conserved energy manifests as steady phase advance within quantum fields. It is how mass, motion, and space-time geometry reveal themselves as measurable temporal rhythm. At the deepest level currently known, frequency is made of change unfolding within time under stable law. If there were no energy, there would be no evolution. If there were no time, there would be no rate. If there were no symmetry, there would be no conservation to anchor the rate. Frequency sits precisely at that intersection. It is not something the universe is made from. It is how the universe moves. And when you hear a tone, or see a color, or measure a spectral line from a distant galaxy, you are witnessing energy revealing its relationship with time. The rhythm you measure is the universe keeping track of itself.